Welcome back. In our previous segments, we delved into the intricacies of simple harmonic motion, unraveling the nuances of objects undergoing perpetual motion. Additionally, in another video, we examined examples of simple harmonic motion. You can find the links to those videos displayed on the screen. Please watch those two videos before proceeding with this one. In this video, we'll explore a unique example of a system where two masses, denoted as m1 and m2, are connected by a spring, and undergo perpetual motion. To comprehend this problem, we need to grasp the principles of linear momentum, the concept of the center of mass, and the theory of simple harmonic motion. This system is indeed isolated, indicating that no external force is exerted upon it. Not even the frictional force. Therefore, the center of mass of the entire system should remain fixed at one point, as illustrated on the diagram. However, if an external force is applied to the system, it will accelerate in the direction of the applied force, adhering to Newton's laws of motion. When we talk about identifying the center of mass as indicated on the diagram, we're referring to a specific point within the system of two masses connected by a spring. This center of mass remains fixed, regardless of how the masses oscillate. In simpler terms, it's the point around which the entire system balances. Now, taking measurements from this center of mass means that we use it as our reference point. When we measure distances from this reference point, we need to be mindful of the direction. In this case, we use a convention, where anything towards the left of the center of mass is considered negative, and anything towards the right is considered positive. This ensures consistency in our calculations and interpretations. We can represent the velocities of the two masses as v1 and v2. Utilizing these velocities along with the masses of the system, we can formulate an expression for the velocity of the center of mass, vcm. However, given that this is an isolated system, implying the absence of external forces acting upon it, the velocity of the center of mass remains zero. Therefore, we can deduce this expression. We then proceed to derive an expression for the kinetic energy of the two blocks relative to their masses, by squaring both sides of the equation, and multiplying both the numerator and the denominator by half. This reveals that the relationship between the kinetic energy ratio and the block masses is inversely proportional. Next, we'll derive an equation for the displacement of the two blocks in relation to their masses. Initially, we establish two reference distances, referred to as d1 and d2, which indicate the positions of the blocks when the spring is in its natural, unstretched state. This enables us to formulate an equation for the center of mass when the spring is relaxed. By simplifying this equation, we can derive the expression displayed on the screen. Following this, we'll examine a scenario where the spring is stretched, causing the blocks to be pulled. We label the distances by which the spring is stretched for each block as x1 and x2. Here, we merge the original distances d1 and d2 with the stretched distances x1 and x2 to encompass the total displacement of each block. By incorporating these combined distances, we establish a second equation for the center of mass, as displayed on the screen. It's essential to mention that throughout these scenarios, the center of mass remains fixed at a single point. This allows us to measure the distances from the same reference point in both situations. Finally, we incorporate the stretched distances of the two blocks and their individual masses into a single equation. This expression establishes a relationship between the elongation of the spring and their masses. The stretching force applied by the spring to the two blocks is represented by F1 and F2. These two forces have the same magnitude, but differ in direction. However, we will state it as shown on the screen. Next, we will apply Newton's second law to the two blocks, and derive this expression. The oscillatory motion of the two masses can be explained by these two equations. These expressions represent the characteristic relationship of an object undergoing simple harmonic motion. In these equations, the angular frequency of mass 1 is denoted by omega 1, and the angular frequency of mass 2 by omega 2. We will substitute the argument of acceleration into the above function, and express it as displayed on the screen. The quantity inside parentheses equals 1, as inferred from what we derived previously. Finally, we arrive at a particularly intriguing relationship. This illustrates that the magnitude of the angular frequency of the two blocks is the same. However, these two angular frequencies are 180 degrees out of phase. This occurs because the two forces oppose each other. This alignment is crucial, otherwise, the center of mass would not remain fixed. Next, we will proceed to derive an expression for the angular frequency. Since both blocks share the same angular frequency, we will simplify by referring to it as omega. The total elongation of the spring is the sum of x1 and x2. Therefore, the force exerted by the spring on the two blocks, according to Hooke's law, can be expressed as follows. Here, K represents the Hooke's constant. Now, let's apply Newton's second law of motion, and express these two equations as follows. The hallmark expression of simple harmonic motion establishes a relationship between acceleration and displacement, as shown here. We will substitute the acceleration into the preceding equation and express these two relationships. Let's arrange the two equations and divide both sides by the respective masses. Finally, by combining the two expressions, we arrive at this relationship for the angular frequency of the two blocks. Let's consider a scenario where two blocks of masses m1 and m2 are connected by a spring of spring constant K. Initially, both blocks are at rest, and the spring is relaxed at its natural length, when an impulse is applied to block m2, giving it a velocity of v0 towards the right. Our objective is to determine an expression for the maximum elongation of the spring. First, we need to ascertain the velocity of the center of mass of the system, after the impulse is applied, but before the spring is stretched. The expression you see on the screen illustrates the velocity of the center of mass. This velocity is necessary for calculating the energy of the system at the outset. The spring stretches out when m2 and m1 start to move. Let's represent the elongations of the springs as x1 and x2, and the velocities of masses m1 and m2 as v1 and v2 respectively, at any given point in time. We should remember to only consider forces in the horizontal direction, neglecting those in the vertical direction, as they cancel each other out. Since there are no external forces acting on the system, the acceleration of the center of mass is zero. This implies that the velocity of the center of mass must remain constant. Initially, the velocity of m1 is zero, but it gradually increases until it reaches velocity v0. Afterwards, it starts to decrease until it reaches zero. Conversely, the velocity of m2 decreases from v0 to 0, then begins to increase again. This perpetual motion of the two masses will continue indefinitely. If block 1 moves slower than block 2, the spring will stretch. Conversely, if block 1 moves faster than block 2, the spring will compress. Maximum stretching or minimum contraction of the spring occurs when the relative velocity between the two blocks is zero, indicating equal speeds of the two blocks. Since there are no external forces affecting the system, we can apply the law of conservation of momentum to determine this velocity, denoted as Ve, which is common to both blocks. The corresponding expression for Ve is displayed on the screen. What this tells us is that the velocity of both blocks, when the spring is stretched to its maximum, is identical to the velocity of the center of mass. In the example we discussed, only one block experienced an impulsive force. However, in other scenarios, both blocks may have initial velocities. In such situations as well, the spring will reach maximum elongation or contraction, when the relative velocity between the two blocks is zero. Revisiting this question, at the beginning, block M2 received an impulsive force, when the spring was relaxed, causing it to move with a velocity of v0. Currently, both M1 and M2 are moving with a velocity of ve. However, when we compare the initial kinetic energy of block 2 with the combined kinetic energies of both blocks now, they do not match. This inconsistency violates the law of conservation of energy, as energy cannot disappear. Therefore, this change in kinetic energy should be accounted for as potential energy stored in the spring. With this understanding, let's write an expression for the change in kinetic energy, and equate it to the stored potential energy in the spring. The maximum elongation of the spring, denoted as Xmax, is given as follows. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. In this setup, two blocks are placed on a frictionless surface, and connected by a spring with a spring constant K. Initially, the spring is at its natural length, when the two forces were applied. The block with a mass M1 is pulled by a force F1, while the second block with a mass M2 is subjected to a force F2. Our goal is to determine the elongation of the spring. If we assume that F2 is greater than F1, we can express the net force applied to the system accordingly. However, this assumption is not crucial, and serves merely as a reference point. Alternatively, you can assume the opposite scenario. By applying Newton's second law of motion, we can determine the acceleration ACM of the center of mass of the system. We wanted to find the acceleration of the center of mass because when external forces are applied to the system, the center of mass is not fixed in one place. However, in order to solve this problem effectively, we need to choose a frame of reference. Therefore, we take the center of mass as the frame of reference to solve this problem. All the measurements, including the acceleration of M1 and M2, will be taken from this frame of reference. With that understanding, we can express the accelerations of M1 and M2 as shown on the screen. Now, let's discuss pseudo-forces. A pseudo-force, also known as a fictitious force or inertial force, is a force that appears to act on an object in a non-inertial, or accelerating frame of reference. It arises due to the acceleration of the frame of reference itself, rather than from a physical interaction between objects. For example, when you're in a car that accelerates forward, you feel pushed back into your seat. This sensation is due to inertia. However, from an observer outside the car, they might infer that there's a force pushing you back. This apparent force is a pseudo-force. After considering the accelerations of blocks M1 and M2, and incorporating the concept of pseudo-forces, we can derive expressions for the net force applied to both blocks. These expressions are obtained by taking into account the forces acting on each block, including the externally applied forces, F1 and F2, and the pseudo-forces arising from the accelerations of the blocks. By simplifying these expressions, we can obtain the net force acting on each block in terms of the externally applied forces, F1 and F2, and the masses of the blocks, M1 and M2. The work done by the net forces is indeed equivalent to the potential energy stored in the spring. When the spring reaches its maximum extension, both blocks come to rest momentarily, with their kinetic energy becoming zero. Therefore, at this instant, the maximum potential energy stored in the spring corresponds to the maximum elongation of the spring. After simplifying the expression, derived from the work done by the forces F1 and F2, we find that the maximum elongation of the spring is equal to the sum of the displacements x1 and x2. This means that the total elongation of the spring is the combined distance moved by both blocks due to the applied forces. I hope these examples were clear. Thank you for watching this video in its entirety. I trust you found it both informative and valuable. If you haven't subscribed yet, please consider doing so to stay updated. Until our next video, take care, and goodbye.